Great to see all of you tonight, and I'm really grateful for the invitation from the Natural History Society. I gave one talk last semester, which I had a great time at. I hope everybody enjoyed it as much as I did on scaling in biological systems and why it is that large animals and larger structures in general have notably different behavior than small ones. You couldn't take an ant and scale up to the size of a 1950s monster movie ant and have it still actually function. The poor ant wouldn't have a chance to terrorize anybody because its own metabolism would immediately collapse. It was a fun talk, and it was well outside my field of expertise. I am not a biologist and can't really pretend to be one except on rare occasions like that. So I had great fun. I thank you guys for the invitation. Anybody who was here, I thank you for the time, attention, and great questions. And great to see everybody again tonight. This one is kind of closer to my own field, so if I make mistakes tonight, I can't even blame the fact that I'm pantomiming somebody from a completely different field of science. But what I was invited to talk about tonight is cosmology, the history of kind of the systematic study of the structure and history of the universe as a whole. So back when I was still kind of pretending to be a researcher before I realized that I had the teaching bug to a scary degree, and was probably going to spend the rest of my life teaching classes, which is awesome. The field I was researching in was cosmology, was the large-scale history of the universe. In particular, we were hot on the trail of some things called topological defects of the early universe that we were absolutely certain was the best candidate out there for the thing that had caused the initial fluctuations that would eventually collapse to form galaxies and stars. And then a satellite called, a satellite whose name I'm suddenly blanking on, Cosmic Microwave Background Explorer. What's that? No, it was before WMAP, actually. Okay, a satellite whose name I'm forgetting. I was pretty impressive because it gave us such terrible news. Found out that everything that we thought we were working on turned out to be absolutely false. So my friends and I did not go down in the history of cosmology except as a minor and embarrassing footnote. But still, it was a really fun field to be working in. So what we were figuring was somewhere interspersed among all the other lectures that Natural History Club wants to put on this lecture, we might do a series of 2 or 3 lectures on cosmology. So we start out tonight with, a topic that makes me almost wince when I write it as the topic of the lecture, ancient astronomers. Why do I wince? Because it sounds like something that you see on the History Channel now that the History Channel standards have slipped so low. Ancient astronomers. Did Bigfoot construct the Egyptian pyramids? But frankly, as of a few years ago, before I started doing a lot of physics 10 classes here, by the way, how many people are or have taken a physics 10 class from us? All right, very nice. But yeah, before I started getting involved in physics 10, where we get to explore aspects of physics that we don't normally have time to think about in our everyday life, man, I would have told you that up until about the time of Copernicus and Galileo, there was no serious astronomy going on. I mean, you hear about the ancient Greeks and Egyptians, and that's just people standing around in togas, looking silly and trying to sound profound. I was entirely wrong about that. It turns out that there was first-rate science, both observational astronomy and a really clever series of deductions that they could make from those observations, going on a long time before blinded modern-day physicists like me might have realized such a thing was happening. In particular, so there's the large-scale structure of the universe, which we will see again as we move on through this lecture series. I'm kind of figuring tonight we will cover the ancients and get up to hopefully Copernicus and Galileo. For part 2, we might do Copernicus and Galileo on through the discovery of the measurement of distances to stars, the understanding of what the hell a star is, how does nuclear fusion work, the discovery of distant galaxies, and Edwin Hubble's discovery of the expansion of the universe. Maybe get us up about 1960 or so when they discovered the cosmic microwave background. The thing that, oh, COBE, there's the name of that satellite, Cosmic Background Explorer. I had the words, I just couldn't figure out how to string that together into an acronym. The things that the COBE satellite broke all our hearts by measuring. Actually, the COBE results were freaking beautiful. It just wasn't the exact results that we had been expecting to see. But the discovery of the cosmic microwave background in the 1960s could be a good goal for that second talk. And for the third one, well, you've heard of dark energy, dark matter, cosmic inflation, all the stuff that's going on right now. I could bring in the LIGO discovery of gravitational waves, and kind of the third one will be the one where I get to play a cut-rate Neil deGrasse Tyson. But even a pale shadow of Neil deGrasse Tyson is fun to do, so I'm looking forward to that too. All right, so backing off from the large-scale structure of the universe as a whole, well, our study of the universe is going to start with the ball of rock that we're standing on. Now, you know that the Earth is a sphere. There's a nice picture of the Earth from space. How long have we as a species, how long has humanity known that the Earth is a sphere, or even known how big it is? When did we first figure that stuff out? What would be the answer that I would be trolling for if I thought that educational standards were still as benighted as they once were? What did we once tell you was the answer to that question? Christopher Columbus in 1492. Everybody told him the Earth was flat. He was going to sail off the end and get eaten by dragons, but he was this wonderful, heroic visionary who knew better and bullshit. Not only was Columbus the farthest thing in the world from a hero, but he also actually knew less than most of his contemporaries about the size and shape of the Earth. Everybody knew the Earth was a sphere at the time. We don't mean everybody. There were people who never given it a moment of thought. There were people who were convinced that it was a triangle or something like that. But everybody who had any business navigating ships for a living, everybody who would have advised Queen Isabella on whether or not to fund the expedition from this crazy guy Columbus, they all knew damn well the Earth was a sphere, and they knew how big it was. That knowledge had never been lost because it was incredibly useful for navigation. When it had first been found, well, actually, about 1,800 years before Columbus. Possibly longer than that. If you're going to ask who was the first ones who seemed to be convinced the Earth was a sphere, some people say the poet Homer in the Odyssey wrote lines that made it clear that he and his friends thought the Earth was a sphere. I don't know. I mean, the Odyssey is kind of a long poem that needs to be translated from Greek. It's hard to tell whether he was talking metaphorically or realistically or what. That would have been at least 800 BC, though. If so, possibly longer ago. Nobody really knows when Homer lives. The mathematician Pythagoras, who was about 500 BC, at least some of the Greek biographers in the centuries after that said Pythagoras was the first one who argued the Earth was a sphere. But we only have the biographer's word to go on. We don't have any direct source from Pythagoras. The first person who we know was convinced the Earth was a sphere was Aristotle. And it looks like some of my formatting of this thing got a little bit warped as I was moving the files over from one computer to another. But Aristotle, I think you know the philosopher Aristotle, the disciple of Plato, who was the disciple of Socrates. One of the most famous philosophers of all time, and actually a pretty smart guy, although later on I'm going to be arguing that his views on physics were foolish dreck that needed to be outgrown. But it wasn't actually his fault, it was just that about 1,800 years later, it was more than about time to start moving physics beyond what Aristotle had thought. However, Aristotle lived in about BC 350 is about when he was doing most of his work. And he didn't discover that the Earth was a sphere, but he presented a clear series of arguments that sounded like it was the consensus of the whole scholarly community at the time. So that pretty much everybody knew the Earth was a sphere. How did they know it? A few different ways. Distant objects drop below the horizon. As you're watching a ship sail away across a smooth ocean on a clear day, you're going to see the ship disappear from sight from the hull on upward to the top of the sails before it actually gets so far away that your eyes are not sharp enough to resolve it anymore. So if you got good eyesight, you can say, nah, I should still be able to see that ship. In fact, I can still see the flag on the top of the sail, but everything below that is dropped below the horizon. Or if looking at ships and trying to tell the flag from the hull is tough, you can say if there's a lighthouse with a series of lights, one that's 10 meters above the water level, one that's 20, one that's 30, you'll notice as you sail toward that lighthouse at night, you see the top one first. It emerges out from under the horizon, then the middle one, then the bottom one. Their argument for that, of course, was that, hey, that makes perfect sense if the Earth is a spherical surface. So they said, all right, that strongly suggests that can work very well. That strongly suggests it's not bad. That the Earth is a sphere, and as you're sitting here at one point on it, your line of sight is limited by the horizon, and anything sailing away from you is going to drop below that line. How many of you are in Physics 4A right now? How many of you did that problem with the tower in Dubai, I think, and how far away from it you can stand and still see the top of it? It's exactly the same problem, and Aristotle was aware of that, and that was one of his strong arguments that the Earth had to be a sphere. Another one was the elevation of stars. As you travel south, well, let's see, this is the axis that the Earth rotates around. Now, he did not know the Earth was rotating on an axis, but if this is the axis through the North Pole and the South Pole, the star Polaris is just directly up along that line, which is why as the Earth rotates, the entire sky seems to rotate around Polaris from our point of view on the moving object. So he said, well, if I'm standing here at my house in Athens, when I look to Polaris, it's going to be a certain angle above the horizon, and it's always going to be that angle above the horizon. As I move farther south, though, my horizon line shifts. Polaris is still straight off in the same direction as before. So the angle between Polaris and the horizon is going to get smaller. Polaris is going to drop toward the northern horizon. On the other hand, stars are going to appear in the southern sky that I have literally never seen before. Anything that was below this horizon line at my own old home in Athens, man, if I go and I start exploring Africa or something like that, I'm going to see entirely new stars that I had never even noticed before. Stars that used to just barely rise above the horizon for a few minutes a night are now going to do a pretty decent arc, carrying them well above the horizon. Again, Aristotle realized that the only interpretation of that made sense to him was that the Earth was a sphere, and in fact, he phrased it pretty well. He said the Earth must be a sphere that, so he said there are stars seen in Egypt and Cyprus, which are not seen in northerly regions. The Earth must be a sphere, as he put it, of no great size, for otherwise the effect of so slight a change of place would not be quickly apparent. I mean, I like that argument of limiting cases and what happens as one measurement gets way bigger or way smaller than another one. That would be pretty decent thinking for a modern scientist. So, if I said that the only thing that ancient philosophers knew how to do was look good in the toga, then I was entirely wrong. All right, what was one of his other arguments that the Earth must be a sphere? Well, he had a whole system of physics. Now, as I told you, Aristotle's physics was not actually right. It was very ingenious, but pretty much nothing about it was actually right, as it turned out. Galileo, 1,800 years later, was going to have to essentially start a lifelong rant to get people's attention focused on the need to rethink Aristotelian physics from the ground up. So Aristotle later in a physics class kind of becomes the bad guy that you need to defeat. But I gotta say, he did a damn good job of starting people thinking systematically about the way the universe works. Now, what was his thought about how the universe works? Well, he would have described it in terms of the classical elements: fire, air, water, earth. I've got a Gary Larson cartoon over here, which is illegible pretty much, but this is early chemists describing an even earlier system of elements. This is the first dirt molecule. It's a ring of DE symbols, and their periodic table over here has one element, dirt. So Aristotle was a little bit beyond that. His periodic table had 4 elements. Actually, it had 5, but I'll tell you about the 5th one in a little while. All the matter directly around us, he thought was made of those classical 4 elements. So why did that help convince him that the Earth should be a sphere, that was the natural shape for it? Well, he had a well-thought-out system of rules for how each of these elements ought to behave, and his rules for Earth, and by Earth he didn't mean the planet, and he didn't just mean necessarily dirt, but he meant anything made out of solid matter. So you'd say, all right, any solid matter would be the element of Earth in Aristotle's scheme. And how did he think solid matter should behave? Well, he thought that it should try to get as close as possible to the center of the universe. Now, right away, you can say, wait a minute, the center of the universe? What the hell is he talking about? This planet's not the center of the universe. Well, he thought it was. So he thought that it's natural that we're standing on a sphere, because what's going on is all the solid matter in the universe is packed as closely as possible around the center. And that's going to pack it into a sphere. So he said, even if I hadn't observed the horizon lines and the stars rising and setting as I move north and south, I'd be convinced the Earth was a sphere just because there's no other natural shape for it. Now, his physics, I said, was entirely wrong. His conclusion, though, was true. The Earth is a sphere, or it's pretty close to a sphere, it's not a perfect sphere. And those other arguments were, pretty good ones. The ships disappearing below the horizon, the sailors sailing north and south across the Mediterranean and seeing different stars. The person who really cemented this, though, who not only definitively showed that the Earth was a sphere, but was able to measure how far around it is, which was a pretty cool accomplishment for those days, was this gentleman, Eratosthenes. He was affectionately, or maybe jealously, known by his peers as Beta. They said Eratosthenes was the second best in the world at every field of endeavor. He was the second best poet. He was the second best actor. He was in his youth, he had taken silver medals at the Olympics, apparently. He was second best mathematician. I'm not sure. Was it? Yeah, well, you've heard of the sieve of Eratosthenes, possibly, if you're a math buff yourself. So the sieve of Eratosthenes, which was an early algorithm for finding prime numbers, this is that same Eratosthenes. He was the second best mathematician, apparently, because Archimedes was alive at the same time he was, and Archimedes took the title as the best mathematician in the world. But for somebody who is close to world class in everything, he had the ideal job. He was the librarian at the Great Library of Alexandria in Egypt. So he had been born in Greece, but he had crossed the Mediterranean, moved to Egypt, and become the librarian at the Great Library. In his capacity as the librarian, he ran across a curious account written by a traveler from further south in Egypt, from the city of Syene. And this traveler had said, there's this weird thing that happens in Syene that I'd never seen anywhere else. Each year, exactly on the summer solstice, the sun passes directly overhead. Now, what they were used to, being in the northern hemisphere, is that the sun would always be at least a little bit south of the zenith. That's what we get here in Aptos. The sun is always at least about 14 degrees south of the zenith, even at the height of summer. At other parts of the year, it passes even further south of the zenith. But they said, hey, in Syene, and those who are paying attention at home might know that what this means is Syene is sitting right on the Tropic of Cancer, 23.5 degrees north of the equator. But in Syene, on the summer solstice, the sun goes directly overhead. They said the people gather in the town square to look down the well. And why would they want to look down the well? Because the well goes straight down a long ways, and there's water at the bottom. And at this one moment, on this one day of the year, you can look down the well and you see this dazzling reflection of the sunlight, because it threads exactly down the well, doesn't hit the wall, bounces off the water, and comes back up. And they said there's no other time that you can see that in this deep well. So that was the thing that had grabbed the traveler's attention. The traveler wasn't an astronomer, wasn't really thinking about the geometric significance of this, but they were just saying, hey, it's cool. It's a piece of local color. It's this custom you got to gather and stare at the blinding sun down the well. So Eratosthenes started thinking about this, and he says, well, wait a minute, this does not happen in Alexandria. In fact, he went outside on the summer solstice, apparently, and he didn't dig a well. Instead, he put a stick in the ground and made sure it was sticking straight up at a 90-degree angle to the ground. And he said if the sun was passing straight overhead, that stick should cast no shadow. And as he found, it did cast a shadow. Even at the summer solstice at noon, when it cast the shortest shadow of the entire year, it still cast a shadow that was a little over 7 degrees off the vertical. Now, 7 degrees means Alexandria must be at about 30 degrees north of the equator, as it turns out. So it's still kind of a more tropical latitude than we are at. It's further south, but not quite down to the Tropic of Cancer. So you didn't get the sun ever passing straight overhead. And he said, well, how could that be? How could it be that, at the same moment, the sun's rays fall straight down on Said, and they fall at an angle at Alexandria? Well, there's one answer that you could give. If you thought the Earth was flat, well, you could say, hey, if I thought the Earth was flat, that would just be impossible. I mean, here I am in Alexandria, and here I am further south in Said. If the sun's rays are coming from directly overhead in Said, shouldn't that mean they are also coming from directly overhead in Alexandria if I were on a flat Earth? It seems like a good argument to me, so at first glance you'd say, hey, cool, you have just definitively shown that we're not on a flat Earth. The Earth's surface must be curved. However, before I erase this diagram and replace it with the diagram of a curved surface, can you tell me any other possibility? Can you think of any way that even on a flat Earth, you could find the sun's rays are coming straight overhead here, but they're casting an angle over here at Alexandria?
It's straight above the first one?
Yeah, the sun could be straight above Said, and it would have to be not all that far above. In fact, if you measure this angle about 7 degrees, so I've drawn it a little more than 7 degrees on the page here, you could triangulate back and you could figure out how far away the sun was. And this calculation would be no problem for them. If there's one thing that the ancient Greeks and Egyptians were really good at, it was geometry and trigonometry and such pursuits. So, you could calculate how far away the sun was. If you did, you would have gotten a distance of about 6,000 kilometers. They wouldn't have measured it in kilometers. They would have measured it in a unit called stadia. If that sounds like the root of the word stadium, well, the stadium, the athletic field, was named after stadium, the distance unit. One athletic field would be one stadium long. And a stadium was about 1/10 of a mile. So 4,000 kilometers, or 600 kilometers, that's about 4,000 miles. That would have been about 40,000 stadia. So he considered the possibility that meant the sun was 40,000 stadia above us, which is not all that far compared to how far it really is, 100 million miles, or I guess that's about 1 billion stadia. So he considered the possibility that, hey, the sun was this close by object, and he rejected that possibility. He rejected it for several good reasons. Some of them were, hey, he had, he was the second best philosopher in the world. He had read Aristotle, obviously. So, he already knew all Aristotle's arguments that the Earth had to be a sphere. Also, for reasons to do with lunar eclipses, which I will come back to in a few minutes, he also knew that, no, a close-by sun and a flat Earth really would make no sense whatsoever. It would make all of our observations of lunar eclipses into a total unexplainable mess. So I'll show you more about the eclipses in a moment, but he said, no, this is not the answer. I think the sun has got to be a hell of a lot farther away than I've drawn it. I think it's got to be far enough away that these rays really are coming in almost perfectly parallel by the time they reach the Earth. So why is it that the stick in Syene does not cast a shadow and the stick in Alexandria does? Well, of course, it's the answer that we know today is actually true. The Earth's surface is curved. So if this is the Earth's surface, then yeah, put a stick in the ground in Alexandria, put it at a perfect right angle to the ground, and that stick is going to cast a shadow at that same moment at noon on the summer solstice. In fact, if you measure the angle of that shadow, once again, you can triangulate and measure the size of something. You're not measuring the distance to the sun, but if you trace these lines from the stick backwards and see where they meet, well, they're going to meet at the center of the Earth. And again, as always, you do a little bit of triangle trigonometry or geometry, which the scholars of the time were excellent at, and you can figure out how far away the center of the Earth is. In fact, it's even the same number that I already wrote up there. That's 6,000 kilometers, or about 40,000 stadia. That is the distance to the center of the Earth, or in other words, that's the radius of the Earth. Essentially what I've done is I've taken that old diagram and kind of turned it inside out. Instead of a flat surface where the lines converge outward 6,000 kilometers to the sun, I've kind of turned the whole thing inside out. Now the sun's rays are parallel, and those lines converge after 6,000 kilometers at the center of the Earth. So he made this argument, and he claimed that the radius of the Earth was about 40,000 stadia. Or he didn't quite put it in those terms. He said the circumference of the Earth was about 250,000 stadia. Did he get it right? Well, let's find out. I always neglect to keep showing you the extra slides. So here's a much more artistic version than I did of the sun's rays coming in and striking that stick in Syene and that other stick in Alexandria and casting a shadow on one of them. You see them extrapolating back to the center of the Earth. So he concluded the Earth is about 250,000 stadia in circumference. Is that right? The actual measured value of the Earth today, the circumference is 40,030 kilometers. So, I mean, he was right almost exactly on the money. Maybe. It depends on, I mean, you could also say, wait a minute, did you really say 40,000 000 since he wasn't using kilometers? Well, actually, if you look up the units of stadia, well, the problem is the Greeks had one definition of what a stadium was, and the Egyptians had a slightly different definition. It's like, land miles versus nautical miles or something. Eratosthenes had been born and educated in Greece and was now working in Egypt, so we have no idea which of the two units he was using. So, unfortunately, a lot of the original documents of this were lost in one of the many burnings of the Library of Alexandria. The Library of Alexandria was burned down either intentionally or by accident, like 6 different times before it was finally burned the final time in AD 400 something. So a lot of this knowledge has been lost, and a lot of it is you recover a book from one philosopher who's summarizing the arguments of another philosopher, and you're saying, man, I hope this guy got it right, because all the books by that other person have been lost to history. But so it might be that he explained full well which stadium unit he was using. We just don't have that page from the book. But depending if he was using the Greek or Egyptian, he either was like right on the money, within like 0.5%, or he was off by a few percent. But even worst case, given the technology of the time, that was a damn ingenious measurement. So if they tell you that Columbus's contemporaries thought the Earth was flat, no, they didn't. In fact, they could probably cite Eratosthenes as their reason for knowing the Earth was a sphere. For the record, does that mean Columbus knew as much about the size and shape of the Earth as everybody else around him? Actually, he knew less. He knew the Earth was a sphere. Everybody knew the Earth was a sphere. But he had mistranslated a book from an Arab astronomer during the Golden Age of Baghdad. And again, it was kind of a mistake on what kind of units they were using. And Columbus became convinced that the Earth was a sphere whose circumference was about 16,000 miles. No, it's not. It's about 25,000 miles, or 40,000 kilometers. So he thought the Earth was about 2/3 the actual size that it is. This was why he had this crazy scheme for sailing from the west coast of Europe, sailing due west, and he thought he would land in Asia after just a few thousand miles. And yes, his contemporaries did tell Queen Isabella this would be a stupid investment. They didn't tell her it's because he's going to fall off the edge of the earth and be eaten by dragons. They said it's because he's going to starve to death at sea, which is exactly what would have happened if there hadn't been a whole new continent in the way. I suppose could have been, it all ended well, except it didn't, because he was an asshole. But what was this? Okay, I showed a class recently a clip from Carl Sagan, who was talking about that nickname beta that Eratosthenes had. And he said, but in one field, at least, Eratosthenes was alpha as an astronomer. And actually, as much as I admire Carl Sagan, I gotta disagree. Even in astronomy, Eratosthenes was the second best alive in his era. Why do I say that? Because of this gentleman, Aristarchus. Aristarchus was living about the same time, BC 250 or so. He was in Samos, Greece. All of Aristarchus's publications would have eventually come to Eratosthenes at the Library of Alexandria. So we know that there was at least a slow manner of communication between them, even though they were separated by the Mediterranean Sea. Aristarchus wanted to measure the distance to the moon. And I say here, thus the size of the moon. And he tried to measure the distance to the sun, and thus the size of the sun, although he did get that one a little bit wrong. I'll tell you why. Okay. Again, when I was moving the files around before, we had like a brief panic of technical difficulties, and the slides had gotten a little bit scrambled, it looks like. So I was saying, so why do I say, and thus the size of, why does knowing the distance to the moon also tell you the size of the moon? No, let Calvin's dad explain it. Is everybody a Calvin and Hobbes fan, I hope? Yeah. Okay. Some of my favorite Calvin and Hobbes cartoons, Calvin Ball is another favorite theme, but some of my favorites are the ones where he asks his dad a science question. And he never seems to learn better than to keep asking his dad science questions. And his dad's answers are absolutely wonderful and imaginative and wrong. So this is the middle of one where they've been talking about where the sun goes when it's set. I think his dad said, oh yeah, the sun sets in the west. In Arizona, actually, just outside Flagstaff. And it goes on from there. Calvin's asking him in this panel, well, doesn't the sun crush the whole state when it lands? His dad says, oh, nonsense. Hold a quarter up. See, the sun's just about that same size. Well, obviously the sun is not the same size as a quarter. Also, it takes, you can cover the sun with a smaller coin than a quarter, as it turns out. But that's the least of the problems. But you could say, all right, Calvin's dad's onto something here. You can measure what arc the sun takes up in the sky. So if you knew how far away it was, that would also tell you how big it's got to be to take up that arc. Or conversely, if you knew how big it was, that would tell you how far away it's got to be that size. If you do hold your thumb out at arm's length, you say, what things can I just cover up with my thumb? Well, I can cover up something exactly the size of my thumb if I put them in the same location. I could cover that coffee cup, but I got to step back further. I could cover that door, but I've got to step back a lot further. So, if I know what arc something takes up, it's just about, and the sun, by the way, is about half the arc of your thumb. You could hide two suns behind your thumb. Or if you've got an exceptionally skinny thumb, half the diameter of normal, then you could hide one thumb. But the point being, if you know what arc it takes up, then the further away it is, the bigger it must be. Or vice versa, the bigger it is, the further away it must be. So Calvin's dad wasn't entirely on the wrong track here. Calvin, by the way, says, I thought I read the sun was really big. Well, it just shows you can't believe everything you read. Later on, at the end of the same strip, Calvin said, someday I'm as smart as Dad is. Why? What did he tell you now? All right, so let me get back to the part of the show that we were on before the slides scrambling. We should just do this old school of things. All right. So we measured the distance to the moon, and And thus, by the Calvin's dad argument, he could also tell the size of the moon. He measured the distance and size of the sun. How did he do these things? Well, for the moon, he did rely on those lunar eclipses that we were talking about. Yes, we scrambled everything. At the time, now, I actually deleted this at the last minute from that slide of different ways that Aristotle knew the Earth was a sphere. I said that Aristotle knew the Earth was a sphere because he had studied lunar eclipses, and then I checked and made sure I was right about that, and it turns out I was wrong. One of the things Aristotle did not understand was anything about the moon. If you asked Aristotle why the moon was giving off light, he said it's because of friction with the atmosphere as it moves, and that's causing the air to heat up and glow, and that's why the moon gives off light. And if you asked him why the moon then sometimes undergoes an eclipse, he would give a long and complicated and creative and absolutely wrong answer. So, by the time of Eratosthenes, which was just about 100 years after Aristotle, but most of Eratosthenes' contemporaries did understand the phases of the moon, why the moon gives off light, and how eclipses work. Hey, help me out here. Why does the moon give off light? Reflects sunlight, yeah. So this is kind of a diagram where the inner one is showing what the moon's supposed to be doing at each, kind of 8 times a month as it orbits the Earth. The only side of the moon that's lit up, the only side that reflects sunlight, is by some freak of geometry, the side that's facing the sun. So, for example, if I'm standing on the Earth and I'm looking up at the moon at this point in its orbit, I'm going to see nothing but a dark disk. So these outer circles are kind of showing what it looks like from the Earth. The inner circles are showing what's really happening as the sunlight falls on it. So there's no sunlight falling on the moon, but it's lighting up the side that I can't see. So I'm going to see a dark disk. By the time the Earth is up there, or the moon is up there, I'm capable of using a laser pointer. I'm just not capable of remembering that I brought one. Strike that, I'm not capable of using it. There. By the time the moon's up there, the people who are on the Earth looking up at it are going to see a half moon. So that's what's actually going on. That's what they see. Over here, they can see almost the whole thing lit up. At this point of the full moon, they can see the whole thing lit up. Now you might say, man, it looks to me like you should get a lunar eclipse every month. Because what actually happens during a lunar eclipse?
Passing the shadow of the sun.
Yeah, the Earth passes through the moon passes through the shadow of the Earth, yeah. A solar eclipse is when the moon's shadow blocks the sunlight for a moment. And yeah, you'd think both of those should happen each month. There should be a moment when the moon gets in the way of the sun, and there should be a moment when the moon passes through the Earth's shadow, so it goes dark for a moment. That does not actually happen every month because, well, for one thing, the moon's orbit is a hell of a lot bigger than I've drawn. If you take the diameter of the Earth, the moon's orbit, as it turns out, should be about 40 times further away than that. So it should actually be outside this room, probably. So we just didn't have room to draw it up there. And it is not quite lined up in the same plane that the Earth orbits the sun. So most months what happens is the moon misses the Earth's shadow. Maybe it's a little bit on this side. It passes a little bit in front of the plane of the screen. Another month it passes a little bit behind the plane of the screen. But every once in a while it threads perfectly through the Earth's shadow and you get a lunar eclipse. Now, Eratosthenes knew that. Aristarchus knew that. By the way, that was the reason why they did not think that there could be a close-by sun and a flat Earth. Because they said, hey, if the sun was like right here, and now I really am going to scale, I'm saying if the sun was only 8,000 miles above the Earth's shadow would be this gigantic cone that went out like that. And you get a lunar eclipse every month. There's no way the moon could miss that gigantic shadow. And furthermore, the lunar eclipse would probably last like 4 or 5, 6 days because the shadow is so damn big. It would take the moon a long time to get out of it. The fact that that did not happen was what convinced them that flat Earth, nearby sun model could not be true. The Aristarchus found another clever use for lunar eclipses. He said, that's how I can tell how big the moon is. If you look at this and you say, okay, sun, obviously again not to scale, the sun's going to be a lot farther away than that, but the Earth's shadow should extend back from the Earth like that. If you watch the moon pass through the Earth's shadow, you should just be able to kind of almost count as it moves across the sky, how many times its own diameter does it have to go before it emerges out the other side of the shadow? So that would actually be a very quick way of figuring out what the size of the moon is. Now, I'll warn you right now, I'm lying a little bit about how easy it is, but I wanted to get this kind of clean version of the logic up here first, because this is the essential logic to how you figure out how big the moon is from watching the eclipse. You just watch the moon going along, it disappears into the Earth's shadow, and you can say, and then it goes 1, 2. It turns out the moon is about 1/3 the diameter of the Earth. You can fit about 3 moons into the Earth's shadow. So they didn't actually, draw the right fraction there, but you can fit about 3 moons in the Earth's shadow. And Aristarchus was able to measure that. So he concluded, okay, that means if the Earth is about 12,000 kilometers in diameter, as Eratosthenes had found, that means the moon must be about 4,000 kilometers in diameter, or about 2,700 miles, or about 27,000 stadia, or whatever unit you're using. Of course, he was still using stadia. But that should nail down the diameter of the moon. And then, by the Kelvin's dad argument, you say, I also know how big an arc the moon covers in the sky. So if I know how big it really is, I can calculate how far away it must be to cover that arc. And what they got was the moon is about 250,000 miles, or that would be about 2.5 million stadia, or for the civilized people among us, 400,000 kilometers away from the Earth. And that is about 40 Earth diameters. So that's why I said if I was really drawing this to scale, the moon should be about 40 Earth diameters back. Again, pretty first-rate thinking, given the only instruments they had to go on were essentially glorified protractors, where you'd just be kind of dialing this dial around and trying to look what direction some line in the sky was. But they certainly didn't have any magnifying instruments. The only way they had of making measurements from different points on the Earth was a good set of walking shoes. So you could go from Alexandria to Syene to Athens and wherever you wanted to go and make all these measurements. By the way, I did lie to you a little bit about how easy that measurement was. The problem is the Earth's shadow is not perfectly sharp like I was showing it. It's also not quite a truncated cone like this. What happens is as you move back from the Earth, the edges of the shadow get fuzzy. So the darkest part, the umbra, gets narrower, like this diagram shows. At the same time, you can notice this. If I hold my hand close to the board, my hand casts a very sharp shadow. As I move away from the board, you can see the edges of that shadow starting to get fuzzy. If I stand this far away, all right, you notice there's some serious kind of uncertainty where that shadow begins and ends. Now, this just has to do with how far back the board is from my hand. And the moon is far enough back from the Earth, we said 40 Earth diameters, that the Earth's shadow has gotten seriously fuzzed out by the time you get back there. So what they really should be showing here is, yeah, the darkest part of the shadow, the umbra, tapers like this, but the grayish part, the penumbra, actually kind of gets fatter as you go. You would go from the other edge of the sun and trace that. So telling where the shadow actually begins and ends is kind of a trick. In fact, if you look at an actual time-lapse picture of what a lunar eclipse looks like, you can kind of tell. Now, this is not the phases of the moon at different times of the month. This is all taken on the same night, and the moon is full. The moon always has to be full for a lunar eclipse, because the only way the moon can thread through the Earth's shadow is if you're at the part of the month where you're looking straight toward the lit-up side of the moon. So this is a full moon. Starts to kind of have the shadow eat away at the edge of it. Then you get into the place where like it's totally covered and you get that reddish glow from light diffracting around the edge of the Earth. So now it's in the umbra, the darkest part of the shadow. Stays like that for a while, starts to emerge. And again, kind of trying to tell exactly where the fuzzy part of the shadow begins and ends is not easy there. Fortunately, it's a geometry problem. And as I said, the scholars of this era knew their way around geometry problems. So it took Aristarchus a little bit more effort than I was pretending he did a moment ago, but he had no problem compensating for the fuzziness of the shadow. He combined this with some data from solar eclipses to tell just how fuzzy the shadow would get. And he was able to kind of mark the true edges of the Earth's idealized shadow and figure out how many moons would fit in it. All right. Well, so far, that's pretty damned impressive. So if they were making such rapid progress, what did they not understand? Yeah.
Were they able to predict eclipses at that point, or were they just waiting for every full moon hoping there'd be an eclipse?
I think they were still just waiting and hoping there would be an eclipse. I think they had not charted it out well enough. I think by the time of Ptolemy, who I'll talk about in a moment, by the time he had put his system in place with more accurate measurements, then you could predict eclipses.
Yeah.
But yeah, as it was, they understood why eclipses happen, but they hadn't charted the orbits well enough to know when they would happen. Yeah?
When the moon got really, really close, we missed the shadow by like a small fraction or something. Did that produce a full moon?
Well, yeah, then you still have a full moon because you're still basically looking at the lit up side of the moon. But if it goes through that fuzzy edge of the shadow, then you're going to get a partial lunar eclipse.
Okay.
So you can get both full and partial lunar eclipses, just like so.
How do they constantly track how long it took the moon?
You have the background of fixed stars to track it against. So you can say, let me first kind of draw out a picture of all the star field there. And then as you're doing your observations, you can kind of sketch in where the moon is and how shadowed it is against that background of stars. And that would give you a way of telling how far the moon has moved in absolute terms. Because you're right, eclipse lasts long enough that the moon will be moving across the sky because of the rotation of the Earth. Not that they knew the Earth was rotating, but that's a whole other story. But yeah, you can adjust for that by saying, I'm not going to measure it relative to the horizon. I'm going to measure it relative to that fixed star field. Really good question. Yeah?
Were the Mayans better astronomers? Because I think they could predict.
Man, speaking of lost records, if we think it's hard to reconstruct the records from the Library of Alexandria and somewhat hard to reconstruct the later records from the Golden Age of Baghdad, because the great Library of Baghdad was then also sacked by Genghis Khan's grandkid, reconstructing the records of the Mayans, man, the conquistadors did a number on that civilization. We have so few records, it's hard to tell exactly what they knew and didn't know. We do know that they did not calculate the Earth as a sphere. They thought the Earth was actually a flat square, and each corner had a certain philosophical significance to it and stuff. Which means that they probably didn't know what a lunar eclipse actually was. So they probably couldn't predict them, because if they knew that it was the shadow of the Earth falling on the moon, then it would be hard to reconcile with that idea that the Earth was a flat square. So their astronomy was incredibly advanced in a lot of ways, but I think that probably the prediction of eclipses was not going to be one of their strong points. You can say the same thing about traditional Chinese astronomy. Well, that's even more complicated, not because the records are lost, but because there were many different schools of Chinese astronomy that all disagreed with each other. So whenever you find an old writer, you have to say, but he's not saying in the beginning which school he belongs to, but you have to kind of deduce that from the. But at least many people also thought the Earth was a flat square in China. I don't think it was because they were in direct communication with the Mayans, but it's just kind of all right. Square is one of the basic shapes you could try. Because of that, we do know that in Chinese astronomy, since they thought the Earth was flat, they did reach that same conclusion we talked about that Eratosthenes rejected. They said they had noticed that sticks in the ground at different latitudes cast different shadows. And they had said, hey, from that we can triangulate the distance to the sun. And they got that exact number we were talking about. They said the sun was obviously a much smaller and cooler sphere than it really was, because they calculated that it was only about 8,000 miles away from us. Or, I'm sorry, about 4,000 miles away from us. The same as the radius of the Earth, not the diameter. So in different parts of the world, these are all quite sophisticated astronomical systems. The Chinese astronomers had figured out a lot of things more accurately than the Western astronomers, even later in the Golden Age of Baghdad, when there was another big, strong burst of activity centered around Baghdad in the Mideast. Chinese astronomers had a lot of things more accurately charted out, but again, eclipses, I think, they did not realize that it was the Earth's shadow falling on the moon. Eclipses were interpreted in a totally different way as essentially portents and advice from the celestial powers to the emperor. So there was a whole side industry of being the person the emperor would trust to interpret the advice they were getting from celestial powers whenever there was an eclipse or a comet or any other unusual phenomenon. So essentially it was considered inter-office memos of the celestial bureaucracy rather than something that had a direct physical explanation. All right. So one thing though that they did not get was if you had, I told you that Aristotle thought that the Earth was a fixed ball of solid matter at the center of the universe. So not only did they say the solar system was geocentric, that the sun and all the planets revolved around the Earth, they thought the entire universe revolved around the Earth. And hey, by the way, when I tell you that he thought that all the solid matter in the universe had fallen to the center, and that was the planet we were standing on, you have every right to say, hey, wait a minute. Have you noticed there's a moon, and that there's other planets, Mars, Venus? What did you think those were? No, remember when I told you that periodic table of Aristotelian elements was actually short one element? He recognized earth, air, water, fire, and there was a fifth element that he called ether. And according to Aristotle, everything outside the Earth's atmosphere was actually made out of ether. It wasn't made out of solid matter. This explained how things like the moon and the planet could be moving independently through the skies, because one reason that they had for saying the Earth has got to be at rest at the center of the universe was that Aristotelian physics. They thought the only way solid matter can keep moving is if there's continually a force pushing on it. So it seems to make sense. I pull this chair across the ground, but as soon as I remove the force, the chair quits moving. Now, we would say today the chair quit moving by friction. If it was on frictionless ground in a room that had all the air pumped out so there was no air resistance, or better yet, if I just launched the thing into outer space and let it go far from anything that's exerting a gravitational pull on it, and then I let the moving chair go, well, we know now it'll just keep on coasting in a straight line forever. It doesn't take a force to keep things moving. It actually takes a force to stop them, or to speed them up, or to change their direction. Aristotle didn't recognize that. If you asked him why this chair stopped moving, he wouldn't tell you friction. He would tell you, well, duh, that's what chairs do. If you're not pulling on them anymore, they stop moving. And then also would have said, that's what, if the boom were actually made of solid matter, which it's not, then as soon as nobody was pushing on it, it would stop moving, and it doesn't. So it's got to be made out of ether, which has a totally different set of rules. Ether apparently could keep on orbiting in circles forever without the need for any outside force. So he had it all figured out. He had it all figured out wrong, but it was all reasonably self-consistent. But that was one reason why most of the scholars thought the Earth did have to be the center of the universe. Now, I told you that I considered Aristarchus an even better astronomer than Eratosthenes. So far, the two of them seem pretty much neck and neck. They both seem to have done some pretty cool things. However, Aristarchus, well, actually, because my slides are scrambled, let me quickly show you one other thing that Aristarchus did that I should have showed you by now. Where the hell did these slides go? Why are there blank white ones in there? Ha! All right. This was Aristarchus's last attempt to make a really cool measurement. He decided to try to find out how far away the sun was. He suspected it was a lot farther away than the moon, and actually he was able to show it was a lot farther away than the moon. Because he said, as the moon orbits the Earth, remember the phases of the moon, he and most of the others at the time understood that phases of the moon just had to do with which side of it was being lit up by the sun. So he said, I'm going to wait until I see a perfect half moon in the sky. And if I see a 50-50 dividing line down the center of the moon, that means the sun's rays must be coming in straight like this, perpendicular to my line of sight, and lighting up exactly half the moon from my point of view. Now, he said, if the sun were infinitely far away, if it were too far to be possibly measured, then the sun's rays should be coming in parallel to those. Remember, when we were talking about two different cities on the Earth, we did assume the sun's rays are coming in essentially parallel. But he said, well, now I've got a chance to see if they're really perfectly parallel. Because instead of Alexandria and Syene, which are only 500 miles apart, now I'm doing Earth and the Moon, which are 250,000 miles apart. Maybe now I can tell that the sun's rays are not perfectly parallel. So he said, if I wait till I see that full moon, and then I look and tell where the sun is, and if I get another 90-degree angle down here, that would mean the sun was essentially infinitely far away, too far away for me to measure, and those rays are coming in parallel. If I don't get a 90-degree angle, hey, now it's a geometry problem. And once again, geometry problems are no problem if you're a mathematician of that time. So he said, if I don't get a 90-degree angle here, I can triangulate backwards and find out how far away the sun is. So he tried the measurement. Now, I gave you that little slide where I said, what were the measurement instruments looking like? Well, they were essentially looking like glorified sticks with protractor dials on them. I mean, you didn't have really precise CCD arrays and telescopes and all that kind of thing. But with the best measurement he could get from those instruments, what he found was, slides are totally scrambled. What he found was that this angle was 87 degrees. It wasn't quite 90. Since it was almost 90, that still told him something important. It told him the sun is a lot farther away than the moon is. And at least that part he got right. The sun is a lot farther away than the moon. From that 87-degree angle, he calculated the sun must be about, no, not 15,000 kilometers. And not, I owe myself some more zeros here. Well, 15 million kilometers, okay, not 15,000. I won't try to type in the zeros because I might crash the program altogether. And the actual distance to the sun is 150 million kilometers. Pretend it said that all along. But, so 15 million, that is, even his unrealistically short distance, that's a lot farther away than the 250,000 miles, or 400,000 kilometers to the moon. So he knew the sun was a lot farther away than the moon. However, if he had done the measurement a little bit better, this angle would actually be more like 89.7. It would be a lot closer to 90. And the sun is actually farther away than he calculated. It's about 150 million instead of 15 million. So it was not as accurate there as with those other measurements, but it was still, as far as just giving you the hierarchy of what things are much farther away than what, you could say he was still right on the dot. However, that's still not the reason why,
I just have one question, and I'm wondering if you know this, if you might know this, the answer to this, but did he ever try, I don't remember what the name of the city S was, but the sun was perfectly,
going to Syene and doing this on the summer solstice?
No, I mean, what if you tried staying at Syene and waiting for a moment where the moon was sort of at a gibbous or a crescent, I don't know which one it would be, but to a point where it would be perfectly, like it would make a perfect right angle to the sun.
Well, let's see, the time that the moon would, your line of sight to the moon would make a perfect right angle with the sun would be when the moon was exactly half full, not when it was, gibbous or crescent or anything.
Well, I mean, like not, well, in the picture it's like relation to the center of the earth, but I mean in relation to where he's standing on the surface.
But wherever you're standing, and looking up the moon, it's still, okay, I would say it wouldn't really make a difference in part because the entire Earth would be considered almost a point on the scale of this diagram.
Oh, right.
Whereas the moon's really a lot further away than that. So standing on a different point on the Earth wouldn't really make all that much of a difference. A good thought, but yeah, I'm leaving myself open to that by doing these out-of-scale diagrams there. But yeah, it's the moon is far enough away that you can walk wherever you want on the surface. You're still going to get pretty much the same measurement.
Okay, thank you very much.
All right, so why did I say he was the greatest astronomer of the age? Well, it's the answer to that question of what object lies at the center of the universe. Aristarchus actually was one of the few who said that the sun was the center of the solar system, that the Earth and the other planets orbit around the sun while the moon orbits around the Earth. So he was saying there's not one center to the solar system, or not one center to every orbit, but you can have different objects orbiting different centers. Now, a lot of people right away said, man, that's just kind of crazy and inelegant. Why would you want some things orbiting the sun and other things orbiting the Earth? You know, they didn't understand the force of gravity yet, so a lot of people just said, man, that's extravagant and unnecessary. Why are you making this overly complicated model? Others pointed out a very good point. They pointed out the lack of stellar parallax. Now, what do I mean by parallax? I mean the phenomenon where if I move around from one viewpoint to another, objects in my field of vision will seem to change position. For example, you do that. But right now, that chair is lined up with that corner of the wall back there, as far as I can tell. Well, now it's not. Now it's lined up with the clock. So as I move back and forth, these foreground objects will seem to shift their position in my field of vision relative to farther away things, or just relative to an absolute coordinate system I set up. I can say, well, I'm just going to say that's my y-axis, and as I move around, the chair is going into different quadrants in my coordinate system. Now it's on the y-axis, now it's left of the y-axis. I can measure the angle to the chair. So that is parallax. If you move around, then things will seem to shift their